Okay, it's time now. Welcome everyone to PASCOS cosmology session 3B here. And this is Jiajun Zhang from IBS as the convener for this session. So the first talk comes from Fabrizio, and he will talk about dark sector to restore cosmological concordance. So please, Fabrizio, it's your time.
Thank you so much for the introduction, and thank you for the organizers of this conference and for the opportunity to talk. This morning here in Boston tonight, we heard about axions in string theory. Now this talk moves away from the from a more formal setup, but I will still discuss axions and possibly in their role for cosmological tensions. So indeed, this talk will mostly focus on cosmological concordance, and it's based on work that I've done here at Tufts University in collaboration with Idamar Alali and Mark Hertzberg. They are both talking at this conference, so stay tuned for their talks. And it's also partially based on previous work that I've done here at Tufts with Mark Gonzalez and Mark Hertzberg, and with collaborators in Spain, Guillermo Ballesteros and Alessio Notari, and partially is also based on older work with other collaborators in Spain. All right, so let me jump into the topic by recalling a bit of the basic lambda CDM model. So as we know, our current effective understanding of our flat universe is based on a 6 parameters cosmological model, which should be thought of as kind of an effective model. This is known as lambda CDM, and it's based on 6 parameters. So those parameters are free to vary in a cosmological fit when one does a fit to data. And for example, these are the CMB and isotropy data. And usually the values of these parameters are inferred by doing a numerical fit to cosmological data, such as in this case to CMB data. As you can see, the fit of this simple 6 parameters model is wonderful to the data. And other early universe probes, such as barren acoustic oscillations, large-scale structured data, they all show great agreement with Planck data, assuming the lambda CDM model. Now, there are other ways to measure parameters, some at least of those parameters, that are more direct and so, in a sense, more model independent. They rely on late universe probes, or I should better say later universe probes, since not all of those probes are really late universe, meaning today. So one such parameter that can be measured more directly is the Hubble expansion rate today, also denoted as H0. And this can be measured via the so-called distance ladder method, which employs supernovae, measures the distance redshift relation of supernovae, calibrated, for example, with Cepheids, as done by the SHOES collaboration, or by tip of the red giant branch stars, as done, for example, by CCHP collaboration. Other methods to measure the Hubble expansion rate today are time delay in gravitational lensing and gravitational waves. Now, another quantity that can be measured in a more model-independent way, in a sense, is the S8 parameter. This actually is just a combination of the sigma 8, which is the amplitude of matter fluctuations in a sphere of radius 8 megaparsec over small h today, and omega m, which is the relic abundance of non-relativistic matter in the universe today. So this combination, which is called S8, is measured by, for example, cosmic shear surveys, such as the ones that I listed here, most recently, for example, DES. And again, if one wants to get an intuitive picture of what this sigma 8 is, then it's enough to look at the power spectrum. This is the power spectrum of matter fluctuations as a function of k, the wave number. And you can see that there, I drew here 2 lines, which denote the range of values of wave numbers that are probed by those cosmic shear surveys. So the amplitude of fluctuations on this scale is usually parameterized by this quantity S8. Now, I say that this is more model independent, but the big caveat here is that actually there is model dependency. So when modeling the nonlinearities, so in fact, these cosmic shear surveys, they also need to assume some specific cosmological model to extract the value of S8. All right, so these two quantities, these two parameters in a sense, can be measured both, can be inferred both with early universe probes such as CMB, and they can also be measured more directly by other experiments. Now, in an ideal universe where, I mean, in a satisfactory situation, if the situation were satisfactory in those measurements, we would have those late and early universe measurements would have to agree, right? Instead, what we find is a disagreement in the framework of the lambda CDM model with respect to both the Hubble parameter, the so-called Hubble tension is represented here. This plot is adapted from this reference, where you can see mainly a disagreement between the early time measurements of Planck based on CMB and isotropies, assuming lambda CDM, and the direct measurement of the Schuss collaboration. Those two measurements here are in tension with each other at the level of 4.2, 4.4 sigma, depending exactly on which value you take for Schuss. And the situation remains similar when you include other early universe probes, such as BAO or effective field theory of large-scale structure here on the early time side. And when you include also other late time probes, such as time delay in gravitational lensing. So overall, this amounts to a larger than 4 sigma tension, which can be considered a strong tension between these two results. There is another tension on S8, which is milder. As you can see here in this plot, this is the value inferred from Planck. And these are values inferred from cosmic shear surveys. So this is a paper from 2020. There are updated results from DES year 3, which came out recently. But you can see in this 2020 combined region with combined constraints with DES and Kids and Viking, there is a 3.2 sigma tension between those measurements of S8. And the tension oscillates from 2.3 sigma in the latest DES report to 3.2 sigma in this combined dataset. So no explanation due to systematics in measurements has come out until now, and that motivates the search for a new cosmological model with additional ingredients that can fit both late time probes and early universe probes better. And so the goal of this talk will be to describe new cosmological models beyond lambda CDM in which the tensions can be alleviated or even solved. In that respect, a very promising strategy for the Hubble tension was proposed back in 2018, and it consists in increasing the energy slightly before recombination, before the epoch of recombination, with the aim of lowering the sound horizon inferred from the CMB. Now, this leads to a larger value of Hubble, whereas whenever the extra contribution to the energy density dilutes faster than radiation. And this faster than radiation is essentially to keep the photon damping scale fixed. So adding only extra relativistic degrees of freedom is not enough to solve the tension. This has been shown already by Planck 18, and you can also see this one of these papers too for an updated fit to the data. However, the crucial point of this solution is that in order to keep angular scales fixed, one has to simultaneously adjust the dark matter abundance, and in particular, one has to increase the dark matter abundance, as well as shift other cosmological parameters. And this turns out to affect the fit to large-scale structured data and exacerbate the S8 tension as well. A notable example in this direction is the so-called early dark energy scenario, where you have a scalar field with a periodic potential of this kind. And what happens is that when the Hubble rate is much bigger than the field mass, then the field is essentially stuck in its potential, and it behaves like some kind of dark energy. And once the Hubble rate drops to below the field mass, then the field starts oscillating and behaves like a fluid with an equation of state which is larger than that of radiation if the potential is flat enough. In this case, for example, it's a cubic, it's a cos cube, and so the potential is flat enough to allow for a large equation of state parameter. Similar scenario is called the new early dark energy, where there is a phase transition in a scalar field. Now, the trouble with this scenario has to do with what I was saying before. You can see that once the large-scale structure data are included, these are extracted using the effective field theory of large-scale structure applied to galaxy cluster surveys. You can see that the values of the H0 parameter extracted within these models are significantly close to the value that would be extracted within lambda CDM. So the red curve is the one that includes the large-scale structure data without the shoes prior. You can see that this is essentially the same measurement as in lambda CDM. So the model doesn't per se improve on lambda CDM if you include, doesn't significantly improve on lambda CDM once you include large-scale structure data. And similarly, you can see here that this is due partially to the S8 tension being exacerbated in these models. As you can see here, a comparison between the matter power spectrum in early dark energy and lambda CDM. You can look at the green dashed line here. They coincide at early time, but in the crucial region, EDE has a higher amplitude of matter fluctuations, which is exactly what we don't want for the S8 tension. And these plots are taken from the very nice works in 2020 by these collaborations. You can also see other works, other very nice works that discuss more in detail these issues in EDE and new early dark energy models. Now, the idea that we have to restore concordance instead is the following. What if this additional dark matter component implied by EDE and new early dark energy is in the form of scalar dark matter, or I should better say pseudoscalar dark matter as a possibility? Now, why is this an interesting question? Because axions and in general scalar dark matter has a scale-dependent sound speed. So it behaves like cold dark matter on large scales, but on for smaller wave number, for wave numbers which are larger than a so-called axion genes wave number, which is given here, the behavior of axion or in general scalar dark matter is very different from CDM. In particular, the growth of modes with those wave numbers is suppressed. And this suppression of the growth of structures is precisely what one needs in order to address the S8 tension. So one can hope that by including such a component, models that solve the Hubble tension can also simultaneously solve the S8 tension without being constrained by the S8 tension. Now, it's our task here to show that this is indeed the case. But first, let's recap some. Let's say that there are indeed constraints on axion dark matter, on ultralight scalar dark matter. These are taken from the latest update from this collaboration. One can see here this collaboration took data from Planck 15 plus if both galaxies are analyzed with the effective field theory of large-scale structure. One can see that in the mass range below 10 to the minus 27 electron volts, only less than 2% of axion dark matter is allowed by this combination of data set. Whereas in this mass range above 10 to the minus 27 electron volts, larger fractions are allowed. Those larger fractions can play a role in the S8 tension. And in this mass range, our work improves on these constraints since we also use Planck 18 plus BAO data. So the idea to restore cosmological concordance is then to consider a decaying dark energy fluid. So a new model, a new cosmological model, which we call dark sector model, with two components. One is a decaying dark energy fluid, similar to EDE and new EDE, that has a dark energy-like equation of state at early times and transitions to an equation of state which is larger than 1/3. We fix 2/3 as an example. It also has an ultralight axion component with the standard axion potential, not cubed, which would be a tuned axion potential. This is a standard axion potential, and generic initial conditions. Such a model introduces 3 extra parameters to lambda CDM at fixed axion mass, the fraction of energy density at the redshift of the ED transition, NED-ED transition, FDDE, the redshift of the transition, ZDDE, and the relic abundance, the fraction of the dark matter in axion today. So this is the ratio of the relic abundance of axion to the sum, to the total relic abundance of dark matter. In order to assess how this model fares with the Hubble tension and the S8 tension, we have to implement this model in class. And this is done by merging the publicly available codes trigger class and axie class, and then using MontePython to run a Monte Carlo Markov chain analysis. And we tested our model using different combinations of dataset to make sure that the model, that the inclusion of priors is consistent. This is a very important point in our work. So we use the first and early universe datasets, which include only Planck 18, baryon acoustic oscillations data, and both galaxy service data analyzed with the effective field theory of large-scale structure using the PyBird likelihood. We then included the prior on S8 from the measurement of kids and from the combined analysis of kids and Viking and DES, which I was referring to before. And then finally, we include late universe data using the Pantheon supernova dataset and the SHOES prior. As a caveat, I would like to remind that the prior is derived assuming a certain model. So we are assuming that it also applies to our model. All right, so let me go to the results quickly. Here I'm fixing the axion mass to 10 to the minus 26 electron volts based on the previous reasoning. And you can see here the situation for different data sets. The orange curves are for lambda CDM and the blue are for our dark sector model. You can see that when we include only the early time data set, the tension with the SHOES measurements, whose 2 sigma bound is here, is reduced to below 3 sigma without using the priors and with the effective field theory of large-scale structure. This is in stark contrast with the situation in lambda CDM and in ED and NED models. And once we include the priors, which is now consistent since the tension is at the level below 3 sigma, you can see that the decay in dark energy component is detected at more than 4 sigma, and the measurement is compatible now with the model. Let me go now to the S8 tension. You can see here again, when we don't include priors with the effective field theory of large-scale structure, the tension is below 3 sigma, 2.8 sigma. Again, to be contrasted with the situation in lambda CDM and new early dark energy, where it is in both cases above 3 sigma. And once we include the prior, you can see that the ultralight axion component is detected at 2 sigma. And you can see also here that the power spectrum, as expected, is suppressed compared to lambda CDM rather than enhanced. That's why we're able to solve the S8 tension. Overall, once we include all priors, this is the situation in the S8 H0 posterior space. You can see that our model accommodates both the measurements of S8 and H0 by late universe probes, and in contrast with lambda CDM. And the residual tensions is in both cases below 1.5 sigma, both with SHOES and with the measurements of S8, to be compared with large tensions in lambda CDM. And the delta chi-squared is pretty large, around -18, with 3 extra parameters. As a summary, let me conclude by saying that current tensions between the early and late universe measurements of cosmological parameters may be hinting towards new ingredients beyond lambda CDM. Early time solutions to double tension are, however, constrained both by large-scale structure data and at the same time by the S8 tension. But we presented a dark sector model with an oscillating scalar dark matter component that can address both tensions and thus restore concordance. Open questions in this framework are: what about the fundamental physics implementations of this model? What about modeling of nonlinearities in mixed axion dark matter universe? Thank you, and sorry for taking too long.
Thank you, and thanks for the very nice talk. Let's have a very quick question from Owen.
All right, should I go through the, I see some questions in the chat.
Yeah, can you answer the question in the chat?
Right, so you mentioned strongly lensed. You see how decaying dark energy could explain the correlation of H naught with CMB correction. Sorry, I don't have an answer for this question. I don't see how the decaying dark energy could explain this correlation. I don't see the picture. Well, I should download the picture. I think it's, I apologize, but I would say let me continue with further questions. Another comment, a prior NMB is better than a prior. Yes, I agree. That's true. So yeah. So this point is that it would have been better to realize a prior on, when including shoes only. It's better to, it's more rigorous to realize a prior on the magnitude on MB. Yes, I agree with that. This is good, a good idea for future updates.
Okay, thanks for your answer. I think according to the time limit, it's time here. Thanks for your talk again.
Right. Thank you.
Thanks. And let's move on to the next speaker. Dr. Yutoda, can you start sharing your screen?
Okay, I will share my screen.
I think your voice is a bit too low.
Is this okay?
Could that be louder?
Is this okay?
You're still a bit low, yeah.
Sorry, I can't make louder.
Okay, I think that's it. And can you share your screen now?
Okay. Can you see my screens?
I guess the data is transferring now. Yutoda will talk about the Hubble tension with an extra radiation and the neutrino degeneracy.
Yes.
Yeah, the screen is still black. Maybe the data is still transferring. Okay, we can see the slides. Thank you. Please go on.
Thank you. Sorry. Sorry. My PC is freezing. Thank you. Can you hear me?
Yes, we can hear you. Please go on.
Okay, thank you. Thank you for the opportunity to speak today. Today's presentation is based on these papers, collaborating with Osamu Setos. When you take an interest in my presentation, please also read these papers. The lambda CDA model has been successful in explaining the evolution of our universe. However, the tension of the Hubble constant between the measurement of the local universe and distant universe is reported. To solve this tension, several ideas for an extension of the lambda CDA model have been proposed. Among such ideas, today, I'd like to focus on the extra radiation and neutrino degeneracy to solve the Hubble tensions. Among such, and I will treat extra radiation parameter and effective as independent of degeneracy xi, because we consider the possibility of stellar neutrinos or axions under the degeneracies. Through the consideration, I'd like to conclude that the combination of extra radiations and neutrino degeneracies is the promising solutions. First, I'd like to briefly explain what is the hypothesis. In the top red line, assuming lambda CDM model, Planck measurement of the cosmic microwave background anisotropy reported that the Hubble constant is 67.4 kilometer parsec per megaparsec. Other distant observations, CMB, BBN, and BAO also reported around 67. On the other hand, local measurement, CAFI's TRGB or supernovae measurement reported higher Hubble constant around 74. I recognize that this tension indicates the physics beyond lambda CDM model. Next, I'd like to explain how the Hubble constant is derived from the distant observations to explain how the extra radiation solves Hubble tensions. Especially, I'll focus on the cosmic microwave background. We measure the anisotropy of the temperature of the CMB photon. This anisotropy includes the information of the angular size theta star equal R star over dm star, where R star is the comoving sound horizon at the recombinations, and dm star is the comoving angular diameter distance. The Planck team strictly and directly measured theta star equal 1.041 times 10 minus scales. If you substitute these equations, the relation of the cosmic time and redshift, where rho is the energy densities, you can realize that strictly measured value theta star is proportional to the Hubble constant at 0 over square root rho in the early universe. Therefore, when we expect to derive a higher Hubble constant, we should increase rho in the early universe. The promising way to increase rho in the early universe is to introduce extra radiations. So immediately, I would like to talk about the extra radiations. The extra radiation is one of the popular extra components to solve the Hubble tension. The radiation of the lambda CDM model consists of neutrinos and photons. When we introduce extra radiation, the relativistic degrees of freedom takes the neutrino generation 3 plus E minus annihilation contribution 0.046 plus extra component contributions. The left figure shows the results of the Markov chain Monte Carlo analysis with varying the relativistic degrees of freedom. The x-axis is the relativistic degrees, and the y-axis is the Hubble constant. In my analysis, I include the data of CMB from Planck, light curves from Parthenons, baryon acoustic oscillations, and the luminosity distance from RIS. You can find that the extra radiation relieves the Hubble tensions. The right figure is the figure without local measurement from Planck papers. You can see the impact of the local measurements. Although extra radiation is promising, you may worry about the consistency with Big Bang nucleosynthesis. The higher relativistic degrees lead to higher helium mass fraction Yp because the additional components increase the expansion rate of the universe, the decoupling temperature of the weak interaction, and the neutron to proton ratios. From the observation, the helium mass fraction is measured in the orange regions, so higher relativistic degrees is disfavored from the helium fraction measurements. In order to let higher relativistic degrees, we introduce neutrino degeneracies. we use the parameter xi I equal mu nu I over T nu, where I equal E mu tau, and mu nu is the chemical potential for neutrino nu I, and T nu is the temperature of neutrinos. The neutrinos distribution function has negative signs, but anti-neutrinos has positive signs. The main contributions of the neutrino degeneracy is varying the number density of neutrinos and antineutrinos. A positive electron neutrino degeneracies lead to more neutrinos than antineutrinos. And the process P plus nu E bar to N plus E plus is suppressed the N plus nu E to P plus E minus. And then neutron to proton ratio decrease. And finally, helium mass fraction Yp decrease. Varying the number densities by the degeneracy also contribute to the relativistic degrees like this. But today, we consider the case only neutrino degeneracy is less than 0.06, and the contribution to the relativistic degree is negligible because we introduce additional larger extrapolation, assuming such as axions or sterile neutrinos. Next, I will show the results of our analysis of extra radiations and electron neutrino degeneracy model. The result of our analysis is left figures. The blue contour is no degeneracy and the same as the previous figures. The magnitude of the degeneracy is in the order of the greens, gray, red, and blue contour. You can find larger relativistic degrees with larger YPs, but larger degeneracy decrease helium fractions. And non-zero degenerate red or gray contour is greatly consistent with the helium measurements. The best fit values for the varying relativistic degrees with several values of electron degeneracies are summarized in this table. The total chi-square at xi e equals 0.04 is minimized for two reasons. The one reason is helium abundance, which I just mentioned. The other is larger degeneracy required higher relativistic degrees and higher Hubble constant. So the Hubble tension is relaxed. These figures are the result of our analysis without local measurements. Namely, we include the CMB, BAO, and BBN measurements. The red contour is not degenerate, and the blue contour is degenerate. You can find that the Hubble constant achieves 7 in 1 sigmas. This is not enough for the Rees measurement, Gefeit and the supernovae measurement, which reports Hubble constant is 74, but definitely alleviates the Hubble tensions. Furthermore, TRGB measurement reports around 70s and consistent with our analysis. So I think the combination of extra radiation and neutrino degeneracies are promising. Finally, I'd like to summarize today's presentations. The combinations of extra radiation and neutrino degeneracies are the promising solutions of the Hubble tensions. Non-zero degenerates xi e equals 0.04 and extra radiation and effective equals 3.45 is the best fit as a combination of CMB, BBN, BAO, and the local measurements. The model of the particle physics which takes large neutrino degenerates, such as xi equals 0.04, and externalization, such as an effective equals 3.45, is worth constructing. I'd like to close my presentations. Thank you so much for your kind attentions.
Thanks. Thanks for your talk. I think it's now for question and answers. Any questions from the chat board, or if you have further questions, you can also just unmute and talk. I can see some questions in the chat board. Let me just speak them out. A question from Central Park said, can you recast your best fit parameter chi-e equals to 0.04 in terms of the strength of CP violation in electron sector?
So sorry, once more, please.
Can you recast your best fit parameter chi-e equals to 0.04 in terms of the strength of CP violation in electron sector?
Sorry, I can't answer these questions.
Okay, well,
sorry.
Thanks.
I apologize.
And also other questions from Owen. Owen, can you just unmute yourself and talk?
I can do. I'm at the coffee shop though. Okay, so you can read the question in the chat. You know that, if you want, right? It may be easier. So also the previous question of Songtan, it's there in the text, right? But basically the key point is that if we have an independent determination of the age of the universe from globular clusters, which we do have, then like you can basically change the sound horizon and change H0, but this leaves you with a problem in the age of the universe. So it's not enough just to change early universe physics. You also need to change late universe physics. If you believe that age of the universe from globular clusters, I put a reference in the text, okay? Again, particle physicists may not be following this, but but cosmologists certainly are.
Oh, yes.
Okay, any other comments or any other questions?
So maybe I can just say something. I mean, I prefer that we raise hand and then you give us order to save time. But both about this talk and the previous talk, I think it's good that people come with different solutions. But I think what has been very common is that people oversell things. Generally, when we have more degrees of freedom or we have extended models, we have larger contours. And it might result to look like that we are reducing the tensions, but the fact is that we are just inflating the contours and confidence levels. And and the mean values are not changing. I think in both cases of this work and previous work, we have seen such things. So it's good to attempt such works, but maybe it's better to not to call these things as kind of a solution, because practically at the moment there's no solution. We have alternatives. They should be considered, and it's good that we are considering them. But yeah, I think we are doing a little bit of overselling, and maybe we should not do that. Yeah.
Thanks, Amr, for your comment. I think I also kind of agree with your comment here. So all kinds of models we have raised here for explaining the Hubble tension or sigma tension, there are some kind of solution, but there are also sometimes from any sense they are still introducing more parameters. So when we say they can really relieve the tension, we should be more careful. Yes.
Sorry, I know I'm out of my time. Can I answer to this comment since it was referring also to my talk?
Yes, please.
Well, so just as it concerned the model that I presented, it is not true that the value of H naught in our model is not significantly shifted away from the value lambda CDM. It is significantly shifted away, and the error bars are not inflated as much as you were saying. So that's
just the page, I think maybe later you can show that, but one slide before your last results when you show S8 and H0 without combining with the S8, SN, and H0, if you just show that, you see that your contours are practically covering the whole contours of the lambda CDM, right? And your mean value is slightly shifted, which is, again, it is nothing wrong with your model. I'm saying that this is a generic feature for any tongue. Even the Komenikovsky's group had the similar features. But calling this that we are resolving the tensions, I think this is a bit too much. That's the whole point.
Okay, thanks for all the comments and the discussions here. I think we can move on. Next speaker will be Dr. Moto Suzuki. Can you unmute yourself and also start sharing?
Oh, yes.
And Moto will tell us about gravitational waves and the dark sector connecting nanograph pulsar time array data and the Hubble tension. Please move on.
Can you see my screen?
Yes. Can you make it full screen?
Okay.
Yes, it works.
Okay, thank you. So hello, everyone. I'm Moto Suzuki. Today, I talk about the gravitational wave signal reported by the nanograph collaboration and the one explanation by the phase transition in dark sector. This talk is based on the work with Yuichiro Nakai-san in TDLI Shanghai and Takahashi-san, Yamada-san in Tohoku University, Japan. Nanograph is a North American nanohertz observatory for gravitational waves. They use two telescopes. One is West Virginia, and another is in Puerto Rico. And 47 millisecond pulsars is used in total, and they took data from the 2004 to the 2017. And they joined the international collaboration, IPTA. So let me briefly explain about the pulsar timing. So the pulsar is a highly magnetized compact star. In the center, there's a neutron star, and this neutron and it emits the radiation beam, and it's rotating. And this rotation period is from the 1 millisecond to 10 seconds. And this radiation beam is observed as a periodic pulse in the Earth. And in the pulsar timing, they use millisecond pulsars, which has a very stable periodic pulse. And this periodic pulse can be disturbed by the gravitational wave. So this dotted line denotes the expected signal, but this yellow line is denotes the actual observed one. Oh, and this deviation from the expected signal makes the residuals in pulse times of arrival. And in the pulsar timing array, the cross correlation of the residuals is an important quantity to detect the gravitational wave. So now let me discuss about the new signal reported by the nanograph last year. X-axis is the frequency of a gravitational wave, and Y-axis is the timing residual cross power spectrum. And blue, orange, green line correspond to the data fitting by the broken power law and power law. In the orange line, use the first 5 frequency point, and in the green line, uses 30 frequency points. And for the right figure, we can get the information of the gravitational wave spectrum dependence of the frequency and the amplitude. So let me focus on the this orange line, which corresponds to this orange line. In this power law fitting, the gravitational spectrum is assumed to be in this form. And from this figure, we can see that the gamma CP around 5 is favored. And it means gravitational spectrum is almost flat. And besides, from this figure, because the the orange line uses the first 5 frequency, we find that a flat gravitational spectrum around the nanohertz can explain the signal. And there are many possible sources suggested. One is supermassive black holes. This is original target of the pulsar timing array, and cosmic string, primary black holes, or the dark photon resonance by the axion-like particle. And today, what I focus on is phase transition. This is our basic idea. So we consider the dark sector, which completely decoupled from the standard model sector. And suppose in dark sector, at some temperature, first order phase transitions occurs. In the position space, the first order phase transition makes a bubble, and this leads to the gravitational waves. And for the gravitational waves from the first order phase transition, there are 3 possible sources. One is a bubble collision, another is a sound wave, and finally the turbulence. And this gravitational spectrum is parameterized by some key quantities. One is the nucleation temperature. Another is a bubble wall, and also the duration of the phase transition. And alpha prime is defined as vacuum energy density over the total radiation energy density at the T star. And kappa denotes the efficiency factor, which means this is defined by the energy density of the source over the vacuum energy density. The gravitational spectrum today has this form. The terms inside the blue box denote the redshift factor. This scales from the nucleation temperature to the today. And inside the red box, this is made by the square of the duration of times, time the square of the energy fraction going into the source. And for this omega tilde, this depends on the period. But among here, this inside F, this includes the information of the peak frequency. And roughly speaking, these peak frequencies are almost same for these 3 periods. And this peak frequency has this kind of form. Because the nanohertz signal can be explained by the nanohertz, so we can find that the nucleation temperature around from MEV to the Jeb scale can explain the signal, may explain the signal. So while we can discuss about the gravitational wave to explain the nanograph signal, we have to be careful about the remnant in the dark sector. So after the phase transition, we assume the energy goes into the thermal plasma, I mean the dark radiation. And using the entry conservation, this amount of dark radiation can be related to the delta N effective. Because the gravitational spectrum is proportional to the alpha prime squared, from the delta N effect constraint, we have to be careful about the amplitude of the gravitational wave. This is our result. The x-axis is gravitational frequency, and y-axis is gravitational spectrum. And these red dotted or solid line correspond to the gravitational wave produced by the first order phase transition for the different delta N effective. Because the nanograph signal can be fitted by the peak around a few nanohertz, and the amplitude is required to be roughly in this range. From here, we find the delta N effective must be larger than the roughly the 0.1. This is also interesting to the point of the Hubble tension. It can reconcile the Hubble tension. This is another figure. X-axis is the nucleation temperature, and the y-axis is the delta N effective. And we fit the data by requiring the peak frequency is in this value. And we consider the peak amplitude for the three cases: orange, blue, and green. And in this figure, each dot corresponds to the different beta over H star value. And from here, we find the beta over H star around the 10 is favored, and the nucleation temperature around the MEV scale. And this is another figure. We also consider the peak fitting the nanograph data by the peak of the bubble. And as we can see, this is also the same structure, similar result for the previous one. I mean, the beta over H larger than the 1, and the nucleation temperature in the MEV scale. Recently, interestingly, the nanograph also analyzed the gravitational wave signal from the first order phase transition. They also consider the three sources: a bubble plus the sound wave plus the turbulence. And for the bubble contribution, they consider the three cases. One is using envelope approximation. This means bubble surface disappears as soon as it collides, and they also use the thin wall approximation. And semi-analytic means they use the result of the multi-bubble simulation, but in this simulation, evolution of two bubble collision is parameterized by the result from the two bubble simulations. And the final one is a numerical simulation, which this is come from the lattice simulation. And this is one of the results of the nanograph. So three figures correspond to the envelope semi-analytic numerical cases. X-axis the nucleation temperature, and alpha star correspond to the vacuum energy density over the relativistic energy density at T star. And focusing on the 1 sigma contours, we find the data can be explained by the alpha star is larger than about 0.1, and T star is less than 10 MeV. And if we go to the 2 sigma contour, this tells us the T star even larger than the 1 GB can explain the signal. So this is summary. We consider first order phase transition in a completely decoupled dark sector to explain the nanograph data. And we predict the large delta effective, which is larger than 0.1. And this can be measured in the near future. Thank you.
Thanks, Moto. And any questions from the audience? You can just unmute and speak. I have a question. So according to your calculation here, in order to put better constraints on the models or actually really detect those kind of signals, would you expect to see the experiment have a longer period in time, or you want them to revisit the pulsar more frequently or have a more precise measurement of the pulsar timing?
Yes, so you are asking this model will be excluded by which experiment you mean?
Yeah, what type of experiment with longer time?
I think delta effective constraint will be maybe the most viable, maybe. This can be proved by for example, the CMV measurement in the ground.
I see.
Just if I may jump in there, so Keith Olive in his recent paper, he says that N effective or N neutrino, right, should be less than 3.16 at 95% confidence level, right? So at 2 sigma. So it seems to be very tight. Even the central values he quotes are below 3.
Okay.
The reference is there.
Okay.
So this is BBN plus CMB.
I didn't see the detail of this constraint, but in the BBN constraint, I don't know how to treat the I forgot lithium-7 problem. If you forgot the lithium-7 problem, the BBM constraint becomes very BBM constraint will be very significant. Yeah, maybe.
Yeah, I think
I'm
not
not
worried
sure
about
what. We believe this the constraints maybe constraint become more.
It's very strong. It's a strong constraint, right? If we believe it. Okay. Okay, thanks.
Okay, thanks. Thank you, Moto, and also thank for everyone for the discussion. I think we can move on. Thanks.
Okay, thank you.
Next speaker will be Linfeng Li. Would you help start sharing your screen?
Yes, just let me share my screen first. Hold on a sec. Can you hear my screen right? Can you see my screen right now? And also my
yes, it works.
Very good.
So Linfeng Li will tell us about the variant kits, the cosmology, and then exonic solution. So please.
Thanks a lot, and also thank all the organizers for allowing me to attend this wonderful meeting, and nice to visit IBS again, though virtually. We have heard a lot about similar stuff about Hubble tension and also axions. So this saves a lot of time. But now let's introduce how cosmology would look like with the varying Higgs VAV, which is fundamental change of standard model, and also what we can have if we go to an axionic solution. So the talk would be based on these 2 works with this lovely collaboration. Welcome to read more details. But as all of you may have noticed, okay, so lambda CDM is kind of under siege. So our major motivation here is to address some of these. Okay, maybe not completely resolving the problem, but see how well we can go. So first of all, is the Hubble tension. That's well known. So since it's well explained in the previous talk, so as these SA or sigma 8 tension, then I will just leave it there. But also we noticed that the lithium problem that's bring up just like a minute ago, which is a long-standing problem during the BBN. Exactly what that means is the observed value of the lithium-7 abundance actually is like only a third of the theoretical prediction. And such a discrepancy nowadays is like already way beyond the fundamental uncertainties in nuclear physics. So it is a problem right now. Also, we noticed that's a recent emergence of evidence of a non-zero isotropic cosmic birefringence, ICB, which violates parity when you reanalyze the CMB data, which deviate from 0 by 2.4 sigma. So here are like how they look like. So not to mention Hubble tension, the lithium problem. Here is our theoretical prediction. It cannot be very far away, though there are uncertainties. But this is like the baryon photon ratio suggested by Planck. That's how theory predicts, and that's where we are right now, observed. So you can see how bad it is. Similar plots show up before. So this is the weak lensing measurement for sigma 8 and also other parameters, and this is the Planck fit. And also in ICB wise, when you turn on different analysis, and you can see there are clear differences from 0. So let's just in a nutshell, if I'm going to explain the whole idea in one slide and then that's it, it is actually not very difficult to understand. It's actually quite simple. So let's start if we just raise electron mass. Okay, it's not a constant anymore because we're going to change to BeV by only order 1% when the recommendation happens or before. The Hubble tension can be at least alleviated. And the reason why is quite simple. By saying recommendation is actually protons catching free electrons and making excited hydrogen. And you can easily imagine this process. The cross section is proportional to Bohr radius squared. Is like how cross section is defined. And as electron mass goes higher, then the Bohr radius shrinks, and this reduced reaction rates, therefore giving you an early freeze out of recommendation. So if the recommendation finishes earlier, then this means the sound horizon shrinks and so on. Okay, this is like one of the way. Okay, reducing the sound horizon. Therefore, you have at least you are allowed to have a larger Hubble. Of course, if this trends also, if we just go back in time, the changing VAV also grants you the property that the Planck mass also increases. And if this is also true during the BBN, because it's earlier than the recommendation, then it makes lithium problem like greatly resolved. It makes the abundance of lithium-7 reduce drastically. You can name a number of models that can do this, but here we choose to just have a very slowly changing field, a very light one as the axion that changes the Higgs VAV. So there are several reasons. First of all, this introduces you a very long time scale very naturally. So just by setting the axion mass. The light scalar, as mentioned before, it suppresses the structure formation. Therefore, you can at least not go into serious problem in terms of sigma 8. Also, as the inherent nature of axion, this AFF tilde coupling, naturally it's just there, these grant you like non-zero ICB almost for free. So let's go into a little bit more details, but I think this like already well explained. So I'm just like mention it again. So by doing CMB measurement, because we have measured several acoustic peaks very precisely, so actually what we are first order measurement of CMB is actually the angular sound horizon, the theta star here. So it can be considered as R star, the sound horizon over D star. And the early recombination solution is just going to shrink the sound horizon here, because the sound horizon is dominated or like say heavily contributed when it's close to recombination. While increased Hubble at that moment, the vacuum energy like Hubble constant, etc., is not going to affect it much. On the other hand, the D star, the distance of this last scattering surface from us is actually dominated by late time expansion. Therefore, it's not quite affected by changing the Z star, moving it up a little bit by like unit 1 or so. But still, if we want to have theta star fixed, we don't want to violate the Planck measurements anyway. Then this shrinking of R star, because it's fundamental change of standard model, it need to be compensated in multiple ways. One of the ways to simply add in more cosmology constant, and therefore you have a larger H naught. And this, of course, if you go to CMB only, there would be a lot of degeneracy. So minimally, you need to combine it with another, at least one observables. Here, for example, the BAO measurement, barrier acoustic oscillation, effectively is measuring the combination of RD times H. So in this plane, you're actually measuring, or the constraints actually look like this. Since we have right now we have no prior or like a priori knowledge of how big the VAV change or the VAV should increase on top of the nowadays value at that moment. So we just put in different numbers, say 1 to 4%. You can see the benchmarks right here. Actually, they aligns, but in general, you can increase H in this way by like to 0.69, and also in the meantime, omega C increases by a few percent. So as the variant. So if we look at how would an axion do this for us, changing VAV is a non-trivial task, by the way. Let's start with the standard model Higgs potential here. So we have these terms, but since in the standard model we have no idea what they should be, they have new solutions, but it is not illegal to address these terms with an axiom. So right here, I mean, you can consider this as the leading term in terms of a cosine A over F. And without further input, we can consider, or we assign Fa, the decay constant of an axion, with M Planck. And it turns out working pretty well for us. In a more complete model, like say nonlinear SUSY, you can try to write the superpotential this way, and therefore this is the officially how you write down potential. But let's go back to this minimal picture. And without huge conspiracy, these two order one, naturally order one constants, they do not cancel. So once the value A squared over M Planck squared change by order 1%, then we would expect the Higgs VAV change by 1%. That's how minimally this works. Then it's the standard misalignment picture comes in. So as long as the axion mass is less than 10 to minus 29 eV, it stays frozen at the plateau when recombination happens and start to oscillate later on. And the amplitude today get seriously damped, so no longer observable. During the process, since Higgs is a very heavy field, so it always stays in the bottom. So it's basically the axion-driven, the Higgs potential move along the valley. By doing so, we also introduce a sub-component of dark matter because it's a misalignment. This oscillation are zero modes, non-relativistic. So if we parameterize such fraction of axionic dark matter amongst all matter, then we naturally get, when we set this scales, we get a result of order 1%. But this is typically allowed according to previous analysis, and you have heard about that before. It's actually even more, it's preferred. So the reason is already well stated. The dilemma of the previous solution or answer to the Hubble tension is that the earlier recombination, if you go to early recombination to shrink the sound horizon, in order to fit CMB data inevitably, you introduce more cold dark matter, so as baryon. But you introduce more cold dark matter, so the structure formation is actually stronger at the sigma 8 scale. So as this plot indicates that these two models, though having higher Hubble, but in terms of sigma 8 wise, they are even worse. So the Axion has the ability to just chop off the matter power spectrum below the gene scale. So as our simulation shows, the matter power spectrum decreased by a few percent if you put in few or tens of percent, if you put in all the percent-ish axionic dark matter. But that's what we want, and since it's only 1% is still allowed, and we compare our simulation with the known result, and they fit pretty well. So here is just some benchmark points that put in by hand, and you can see in this H0 and S8 plane, eventually they move closer to this ultimate preferred regime, or in a more complete analysis, we just do the Markov chain trick. We show that the Xe-Higgs model turns out to outperform, not to mention lambda CDM, but also the model with a changing VAF, but without Axion, especially in terms of S8, it moves like this is the way that you fit or say suppress the structure formation at the scale. I also want to mention something beyond that. So first of all is the BBN. So of course, BBN can be very complicated, like tens or hundreds of processes like entangled together. Even you look at the simplest ratio, the N/P ratio, as determined by these non-trivial parameters. Okay, it could be very complicated when you change VAF. But in brief, you increase VAF, it changes 4 different aspects. You have a larger Fermi constant or a larger MW mass. That's gonna change electroweak process. Here, the electric process that matters is the MP conversion and also neutron decay. Electron mass is doing the similar, so it mostly all these affect electroweak sector of standard model. Isospin breaking has something to do with nuclear physics, but still mostly via electroweak. But here, the most significant change, especially when we're trying to look at the lithium problem, is the light quark mass on average, which is proportional to the Higgs VAF if we're not changing Yukawa. The reason why is that the nuclear reaction is actually highly sensitive to quark masses, especially when this also means change of the pion, because the pion mass is proportional to the square root of quark masses, and this will make heavy nuclei unstable. So it's shown in this plot. So heavy nuclei, say lithium-7, or like say the one that makes it, the beryllium-7, is actually quite sensitive to quark mass changes. Increasing quark mass, light quark mass, effectively greatly reduces their binding energy. And this is because, as I've said, quark mass increases and the pi mass increases. As the messenger between nucleons, the heavy nuclei become more fragile. And that's how all heavy nuclei production gets suppressed, but unfortunately lithium-7 is the only one that's observed nowadays. So we summarize different effects in this table. You can see that electroweak effects are actually quite moderate, while the significant effect always comes with the quark mass. And by doing some analysis or just a numerical fitting, we find that the ultimate preferred number of delta V during the BBN is actually around 1%, while we accompany with a baryon to photon ratio, or omega B, equivalently from 1 to 3%. But this overlaps with our CMB preferred regime. I'm gonna briefly mention the ICB. So this is quite simple. So as the initial phase, you don't know if it's positive or negative. You just know the absolute value. So as it rolls from its initial value to the nowadays value around 0, then this A at the total coupling breaks parity and it starts to rotate K, the polarization of CMB. And if this beta angle as observed nowadays, if you take it, then it turns out that the A over F, A initial over F is like around 1, a very natural number without fine tuning, so that's good. Finally, you may wonder how we can observe these axions, since this is a very light field, so way beyond reach of the current axion detection experiments, say haloscope or helioscope type. But still, since this change fundamental constant, which is the Higgs VAF, and so many subsequent ones, we can consider this as the experiment monitoring the change of fundamental constants, say the reduced electron mass here. So the current best limit actually comes from the atomic clock measurement, which grants you the precision like order 10 to the minus 17 per year, which is achieved by like monitoring the frequencies like in the time span of 10 years. And this turns out to buy you a limit on the axion mass to be greater than 2 times 10 to the 30 eV. But our model actually the best benchmarks actually stays at like 10 to the minus 29 eV. So this is not quite enough. So we estimated that in order to do so, or like either make some discovery or fully exclusion, we need to go like 1 or 2 orders of magnitude beyond. This is actually achievable by the future improvement of atomic clocks or even nuclear clocks, given the fast progress in this field. So we may expect some fundamental breakthrough within 1 or 2 decades. Also, we may, as alternative, because local measurements always suffer from this fine tuning of the axion phase, but we can also equivalently looking for the deviations of standard model in the sky by pointing to very distant but bright targets, say quasar. So the reason is that by observing the molecular spectra, there are several different modes here, and that the dependence on fundamental physics is different. So it breaks the degeneracy between the redshift and Higgs variation. And here are just how everything looks. We summarize the current observations right here, and also with different axion mass, that's the envelope of the maximum drift that you are allowed. But so far, the constraint is not as strong as the atomic clock ones, but stay tuned. So a brief summary. So I'm gonna just throw all these 2 plots here. So one is the marginalized fit with different axion mass benchmarks. So far, we have especially these 2 are still allowed, and here it just shows different evidences and that they coexist together in this region. A quick review of this talk. The idea is very simple. So higher Higgs VAF by changing the electron mass, therefore you have earlier recombination and therefore allowed larger Hubble. And in the meantime, the nuclear physics component grants you compatibility with BBN at least, and potentially the lithium problem. By going axionic, you are gonna resolve or like at least alleviate the tension in sigma 8. Also grant you the explanation of a non-zero ICB. In the future, this model can be tested in multiple different ways, even from direct observation. So I think that's all. Thank you.
Thanks, Jingfeng. Thanks for your talk. There is a comment in the chat board. Can you see the comment?
Yes, I'm trying to see that. Yes. Okay, the 4.6.
So Owen said, comment there is a 4.9 sigma discrepancy in the dipole inferred from CMB and the distant quasars. This could be added to the tensions at the beginning at face value is more serious than Minami-Komatsu angle.
Thanks for the comment. Yeah, I'll try to read that and maybe add it to my slides and also the paper later on. Yeah, thanks a lot. Is there any other questions?
Any other
Yeah, I
questions?
agree that,
So,
okay.
Can I
Yeah.
ask one question?
Yeah.
So, okay, my question is that how did you treat perturbation when you were fitting your model with the CMB data?
What do you exactly mean by perturbation?
Well, you know, when we feed CMB data, we should consider perturbation. And how did you do that for your model?
I think what we have done is like treat this semi-analytically. So we typically find a fixed point. So we have a starting point, which is the one of the plant fit data, and therefore we calculate the response of this model in a perturbative way, if you want, or that's how we get this.
Okay. I mean, what did you use? You use class or CAMB or CMB fast? What did you use to?
I think we use Axion Camp, a modified one.
I see, I see. So the one which is designed for the Axion.
Yeah, that's
Okay.
that's the fundamental feature. Of course, we also changed the recombination, so we also use RecFast to incorporate.
I see. Okay. I think that could already consider the proper perturbation for this model. Okay, yeah, thank you. And then one comment about Owen's comment. I think these are speculative points. You know, we cannot just, you know, people write papers. Many of them are not really reliable. So yeah, to make something as a real tension, you know, things have to be done independently by different groups and needs to be confirmed. So just speculating that there is a dipole or the correlation between, you know, H0 and CMB dipole, people have been working on this field for decades. And yeah, so we have to be careful by just calling something tension before it is really confirmed by the community.
Yeah, thanks for the comment. I think our goal here is to present the idea that what possibly could happen, and well, following this idea, always people can do better analysis, because we are not real cosmologists. And at this point, I think because the complexity of the data, yeah, it is also you know, it's beneficial to treat it very seriously later on by different groups. But so far, what we do is just present the model or the idea. I think the idea is simple enough.
Yeah, sure. Yeah.
Thanks a lot.
Thanks for the talk, and also thanks for all the comments and discussions. I think we can.
So should I stop sharing right now?
Yeah, I think you can stop sharing.
Oh, thanks.
Thanks. Next speaker will be Takahiro Terada. Can you start sharing your screen? Takahiro? Yeah, okay, we can see you.
Yes, okay. So thank you for introduction. So should I start now?
Yeah.
Okay, so I'd like to thank the organizers for giving me this opportunity, and also thank the audience for coming to this parallel session. But I should say that this topic is rather different from the previous talks, and I will talk about more HepTH-like thing. So this is about inflation in supergravity with minimal degrees of freedom. In the previous formulation, in the previous literature, there was some anomalous production of so-called slow gravitino. And I would like to propose an alternative realization of this kind of scenario without this issue. I will explain this. So as an introduction, I would like to introduce supersymmetry. So this is a good symmetry introduced for the physics beyond the standard model. And I do not go into the details, but this is in principle useful to ensure flat inflaton potential. Of course, this is not sufficient, but this can be the first step of the model building. But as you may know, supersymmetry must be broken in the real world. And even theoretically, if you consider the cosmological setup, then it must be broken by finite Hubble expansion of the universe, and also by finite temperature effect. And once supersymmetry is broken, generically fields receive supersymmetry breaking mass contribution of order the Hubble itself. This is also called Hubble-induced mass. And so since this is the same order of the characteristic timescale of the cosmology, one can expect that if these particles are excited during inflation, then there is a possible observational windows. So this is very interesting, but this is not the topic of my talk today. So I'd like to say that although this is generically masses of the Hubble, it is also possible that some fields can become much heavier than the Hubble and then decouple from the inflationary dynamics. And typically, if you construct inflation model, then there may be other scalar fields in the theory, in the inflaton sector. So you need to sufficiently stabilize its scalar potential so that it does not receive large quantum fluctuations during inflation to satisfy the isocurvature constraints. And this is also useful for the modular stabilization context. Now, if you consider this kind of higher order term in the scalar potential, then after this field develops F-term supersymmetry breaking, this becomes an effective mass term contribution. So in this way, if this cutoff lambda is somewhat lower than the Planck scale, then this can be parametrically larger than Hubble. So, schematically, initially, there may be some fields, some light spectrum here, and they are related by supersymmetry. But because of this, some component can become heavy by SUSY breaking mass term. And after that, the remaining light degrees of freedom form an incomplete supersymmetry multiplet. And this can be described by a constrained superfield. A popular example is the so-called nilpotent superfield. Let's call it X, which satisfies this nilpotent condition constraint. Usually, chiral superfield X is expanded like this. And however, because of this constraint, this lowest leading component, the complex scalar field, is replaced by the fermionic bilinear divided by the auxiliary field. So in this way, the light degrees of freedom is related by supersymmetry among themselves. This becomes its bilinear and vice versa. So this is the nonlinear realization of supersymmetry. So far, so good. And so a natural question may be, how about generalization to fermions? How about decoupling of fermions? I would say this may be difficult from the perspective of the UV completion, to construct this kind of concrete way. And this is partially motivated from what I will introduce in the next slide. However, people already try to consider some kind of this stabilization term and also phenomenological applications of such kind of situation. So let's consider what happens. This is a so-called minimal supergravity inflation proposed by these papers. And so this is a supergravity inflation model with two chiral superfields. Let's call them X and T. And here T contains an inflaton. And there is another superfield which is useful to make the scalar potential positive semi-definite. Then we have this kind of constraint. And this is nilpotent, similarly to the previous slide. And this is orthogonal in this sense. So multiplication vanishes. Because of this constraint, the screen is not responding. Right, so I reshare, sorry, some technical issue. Oh, no, it works. Sorry. So because of this constraint, many components are killed, effectively killed. These are replaced by fermion or auxiliary field. By dashed line, single real degree of freedom is replaced out of two real scalar degrees of freedom initially present. So the only independent and dynamical degrees of freedom are these so-called stabilized Zeno and a real inflaton. And after the super Higgs mechanism, this stabilized xeno is eaten by the gravitino. So the physical spectrum contains only a real single inflaton and massive gravitino and massless graviton. That's all, despite the fact that this is a supergravity theory. Now, more concretely, the model is specified by the scalar potential and the superpotential. So the scalar potential is given by this very simple form. However, this is different from the usual textbook level supergravity formula. This is because of, again, this constraint. Because of this constraint, F term effectively vanishes, so the off-shell structure of the theory is modified. Okay, so let's consider what happens after the inflation in this model. So previously I introduced something strange happens in the F term and the scalar potential changes, but a more dramatic thing happens in the fermionic sector of the theory. Let's look at the gravitino and its longitudinal mode, because longitudinal mode is more sensitive to the supersymmetry breaking. Now, importantly, the propagation speed, limiting propagation speed of the longitudinal gravitino mode, the so-called sound speed mode, is changing, and this is different from the speed of light. This has been studied in a broader context previously, but in this minimal supergravity inflation, this changes more drastically. So we observe some very strange thing. To analyze this system, actually, we do not need to assume inflaton oscillation or whatever, but because the Lagrangian of the gravitino is described by general quantities like energy density and pressure. But nevertheless, to gain some intuition, I draw this picture of the inflaton potential. Now, also for the purpose of easy explanation, let's neglect this term multiplied by gamma matrix. Then this is just a real number. So we can see that there is a sound speed parameter, negative region, positive region, and negative region. This does not correspond directly to the physical sound speed, but this is a parameter in the Lagrangian, so it can be negative. But anyway, after inflation, the inflaton starts to roll down its potential, and surprising thing happens. We can solve the equations of motion of the gravitino Fourier mode, and then you find a solution of the phase space number density of the each mode. Then, so at this moment of the sign change of the sound speed parameter, you see this sharp peak, a sharp rising, like a step function. And this solution is independent of momentum. So this means that, this implies that each mode up to a very, very high energy scale, because it's momentum independent, can be produced, and possibly up to the UV cutoff scale, whatever the UV cutoff scale is. So this can lead to cosmological catastrophe due to the gravitino overproduction. The number density of the gravitinos can be UV cutoff scale cubic, and if you consider the energy density of the gravitino, it can be quartic. So this may be a real cosmological problem, or another interpretation is that since this is so extreme phenomena and it's theoretically anomalous, this is not, by this I do not mean the quantum anomaly as a technical word, but ordinary sense, this is very anomalous. So the effective theory may break down at this stage after the inflation. So the description may not be applicable. I don't know why this screen doesn't change. So let me re-share again. Sorry for inconvenience. However, my main aim is not to solve this issue in this talk. And instead, we propose an alternative model for this inflation in supergravity with the same minimal degrees of freedom without the issue. So we avoid the issue. To realize such a situation, we introduce a cubic nilpotent superfield phi. This is a new constraint superfield on obeying this equation. and this is recently introduced in this paper. Phi is a chiral superfield, and as usual, this is generically expanded like this. But because of this constraint, imaginary part is replaced by other components like fermionic component and auxiliary field and the real part. And the solution of this constraint, I mean, this explicit form of this equation, this relation, can be found in, for example, in this paper or appendix of these slides. But the expression is fairly complicated already at the global SUSY level. So if we go to supergravity, it could be much more complicated. But fortunately, there is a way to reduce the calculation. I mean, we can work in the unitary gauge, then calculation becomes very simple. I don't need to go to the details of the calculation, but we find in the unitary gauge, the imaginary part simply vanishes. This is the imaginary part of the scalar field. And a crucial difference compared to the previous literature, I mean, the orthogonal nilpotent superfields, is that in our case, the inflatine is maintained in this superfield. And also the F term is maintained, not removed by the constraint. Although the main topic is about the gravitino, so I'd like to say that inflation is possible in this alternative model. Otherwise, it's useless. So, okay, we use the cubic nilpotent superfield I just introduced in the previous slide. Then scalar potential is generically expanded like this. In terms of the imaginary part, this is the 0th order, 1st order, and 2nd order, and higher order terms, all the higher order terms vanish trivially. And the coefficients of the expansion can depend on the real part of the inflaton, which is real inflaton, dynamical inflaton. So we can impose shift symmetry. This is as usual in the supergravity inflation literature. So if we impose shift symmetry, these become constant. Now the superpotential becomes, superpotential can be generic. Again, this is not responding. Sorry. I have no idea why this happens. So to proceed further, we should specify superpotential, and then there are several known methods already to construct the inflation potential using only a single chiral superfield, as in our case. So one example is by this paper, and this is just one example, but if we take this superpotential, then the resultant inflaton potential is that of the similar to the alpha attractor model. So then the prediction of the alpha attractor is yellow lines. So it can be consistent with observational constraints by the Planck satellite. Okay, so now I'd like to talk about the gravitino, but this is very simple in our model because now the sound speed of the gravitino mode is same as the speed of light. So gravitino is not slow in our model, then there is no catastrophic or anomalous production of gravitinos related to the sound speed change because it's not changing. Nevertheless, the other contributions to the gravitino abundance there, because which is not related to the sound speed. The cosmological gravitino problem is so severe, so actually there is a problem also in our case, and actually it's somewhat severer. In particular, in our case, non-thermal production is so huge, and we can estimate the partial decay rate of the inflaton into a pair of gravitinos. It is enhanced by this factor if the gravitino mass is much lighter than the inflaton mass. The following story is same as the usual story, so I will skip, but this is very dangerous with respect to the Big Bang nucleosynthesis and dark matter abundance. There are several solutions, like kinematically forbidding the decay or thermal inflation or alpha-d vibration. Maybe the simplest solution is that assuming very heavy gravitinos and say the universe will be dominated by the energy density of that gravitino, but if that reheating temperature is sufficiently high, then it can reduce to the usual wing paradigm if the LSP mass is sufficiently small. Right, so let me summarize. Maybe time is running out. So we proposed an alternative realization of minimal supergravity inflation scenario where there is only a single inflaton, gravitino, and graviton. Very minimal scenario. For this purpose, I utilized this cubic nilpotent superfield. And although there are still standard gravitino problem, in our case, the catastrophic gravitino production related to the sound speed change is absent. So this is my main message. So thank you for your attention.
Thanks, Takahiro, for your talk. I think we can have time for one question here. Any question from the audience, you can just unmute yourself and speak.
There is some chat. We need to. No. Is there any UV completion of the cubic and orthogonal constraints? I guess so. Although I don't have a concrete example to explicitly show that it happens, but in this case, the only decoupled component is the scalar superpartner of the inflaton, the so-called synchlaton. So it is relatively easy to only decouple the scalar, heavy scalar part. So yeah, I think it's possible. Also, this can be, for example, an effective field theory, effective field theory of some of the existing models, like existing models of this kind of setup. If the UV theory only contains a single chiral superfield and without containing stabilizer field, then this kind can happen.
Okay, thanks for the question, as well as thanks for Takahiro's talk and your comments. I think it's thank you for everyone for attending the session this morning. And in the afternoon, we will have our program back from 13:40 in Korea time this afternoon. So thanks all for attending the conference in the morning, and see you in the afternoon. Have a good lunch. See you. Bye-bye.